Okay, my friends, this is going to be fabulous. I am excited. This just came out, Why We Smash Particles, with physicist Sarah Demers. Now, here's what they have to say. This is at CERN's Large Hadron Collider. They created the world's highest energy human-made collisions to explore the fundamental building blocks of the universe. Join Yale professor Sarah Demers as she describes how CERN researchers create and learn from these collisions at the energy frontiers. Now, she's down at Yale. That's right down the road from me, actually. Now, this is what they're going to go through, all of these different chapters, and they're only a couple of minutes apiece. Now, I did leave a very long, detailed explanation of what we do and Dipole Electron Flood Theory, which is here, which is a whole new subatomic model. All right, in other words, hydrogen is not one gigantic proton and one tiny little electron. Both of them have the same charge, only opposite. It's 1,825 or so dipoles, which means they're little bar magnets, but they're round. I will show you this in extreme detail. Okay, my friends, get ready. This is going to be fun. Why we smash particles, with particle physicist Sarah Demers. And they're going to be talking about why do we spend literally trillions of dollars trying to smash these particles? What is the benefit? Why do we do this? Is there any reason for it? Well, let's talk about it, because I also am into smashing particles, only I don't start with the big particles like this, which is a proton. I start with the particles which are light, which is this, which is photons. Totally different, makes much more sense to work in this realm, because these are nothing more than particles of these. They want to get to the smallest particle of these. That's what this is all about, which is these. They are light, but they have never done the light experiments, which we did. And I can show you these experiments. They are quite convincing, and they are done with light. This is light. This is not big proton colliders. And we force them through a Venturi, which makes them crush instead of trying to hit them head on. Because you try to hit them head on, and they got a big rubber field around them, like a big balloon. They go boing, they go boing, they go boing, but very rarely do they go smash. We are going through a Venturi, and there is no way to get out of it other than to smash. Let's show you. Okay, this is going to be interesting. This goes back to 2013. This is Don Lincoln at Fermilab, and he posted this and was talking about these two particles. This fixed one never changes size. The glowy one can get big and get small, has no mass, and it has all the mass. I agreed 100%. And I did contact Don, and we went back and forth a little bit. And here's his other statements, is that the quantum foam, empty space, isn't empty. I said, yes, you're right, it's not empty. It's completely saturated with those particles of light, which I show as particles. They're not nothing. Then he claims that the standard model is most successful. It is not. The only two particles that exist are the black and the white two particles. I'll show you, the muon, electron, neutrino. That's it. Everything else is made of those two. And then he also talks about the dirac, which is exactly right. This is the two smallest particles. And when you break them in half, you end up getting these. This is what it is right there. So these are from our light experiments. This is from actual experiments we did, Rod Warren and me. And this is the results of them. These aren't little doodles and pictures. This one is, because that's from Fermilab, or from CERN. And what they do is they take huge particles, neutrons, protons, smash them together, and they get all kinds of debris. It's a zoo. And the reason is, these aren't just solid particles. These are made of 1823 for a proton, 1824 for a neutron. And when they come together, you just get slammed with all kinds of garbage. That's just everywhere. So they take years and years and years digging through this, plus the equipment to do this is like trillions of dollars by the time they're done. So we're going to get into this and see what you think. Okay, my friends, get ready. This is going to be fun. Why we smash particles, with particle physicist Sarah Demers. Now, this is the Institute of Art and Ideas. They got 303,000 subscribers, and they're talking about how do we get high energy. Protons, what's going on with protons? What about the Large Hadron Collider? Spectacular collisions, particle detectors. All of this stuff is my area. I understand this stuff quite well, and I think you will see that as we proceed forward. Now, I left them a comment because they said, do you believe particle collision is a worthy pursuit? Let us know what you think in the comments. See the full talk, which obviously we will, or I will anyway. Here's what I said. I said, yes, collisions fracture stable protons, big stable protons. They smash them. However, they create large amounts of debris, all kinds of stuff. They call it a particle zoo. We use light. So instead of using a gigantic thing like this, which is made out of this, we use light, which is made out of that. So we used particles of light, which is among the tiniest particles. Photons are made of dipoles, called diracs, which are the muon and electron neutrino held together, the black and the white. And they're held together by the strong nuclear force. The new model is Dipole Electron Flood Theory, and a proton is 1823 dipoles. So this is what a proton is. It's not one big one of these that they can smash and little bits and pieces fall off. No, it's made of this. When they smash these together, yes, they get all over, chunks of this size, that size. It's a zoo. When we hit ours into the Venturi, that's all we started with. So we don't see a zoo, we see exactly what's happening. So now I said we accelerated light through a Venturi. It's also crushed the fields. It crushed it, just like they're hitting them head on. It's the same as hitting head on, but very confined and targeted through the Venturi. The Venturi crush does the same as a collider. Okay, but the collider comes like this and it goes ring, zing, zong, zing, because the fields hit and they can get out of each other's way. Here we're going through the Venturi. There's no getting out of the way. So the crush does the same as the colliders, but it's much more reasonably reliable, very simple. They both smash and crush fields beyond their normal limits of the Casimir field effects, which means they crush fields together. They should never, ever be able to touch. And I believe in our cases, they are actually touching and bouncing away from each other. But if you look up Casimir effect, you'll see. So the head-on collisions are very, very hard to create. The fields oppose each other. Fields like a rubber ball bouncing this way, bouncing this way. They want it to hit head-on. Occasionally they do, very rare. We squeezed the fields through a tuned Venturi that accelerated and crushed them, and there's no way they can get out of it. The muons are fixed size and carry all the mass, it seems. The muon's the black ball, and the white balls, so it says the muons carry all the mass, it seems. The muons are solid, absolutely solid. They're black, and one size fits all only, so they cannot go through the Venturi. They can't get through. They can bang, 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 but what they're doing is pushing the white through. They end up as a sterile muon. The electron bit can get very tiny and flow through as electron showers. That's what they did. Now, we're going to go through and see what they have to say about all these things. How do we get high energy? Protons in the electric field. This is what they're going to go through, which is what we are going to go through. So let's get started. Okay, so here we got heat and energy. Let's talk about that. I asked, what is energy made out of? What is it made out of? What's energy? Energy is a property of an object, not something it's made of. Well, let's talk about that in a second. For example, a pan on a stove can be described as hot, which is a measurement of the thermal energy. Well, what's the thermal energy made of? Adding heat to the pan changes a property, not adding something to it. No, you are adding something to that pan when you heat it up. You're adding weight to that pan. Okay, so here we got another issue. Does heat add weight? Well, yes, it does. No question it adds weight, but they don't understand how it does it. It says, according to HuffPost, a kilogram of water at 100 degrees centigrade is 4.6 nanograms heavier than the same amount of water at 0 degrees centigrade. This is because, this is what they say, because the kinetic energy shaking around the atoms in the water differs at different temperatures. The special theory of relativity also states all forms of energy, including heat, have weight and inertia. Well, every heat is a particle. Heat is actually made out of a particle. If you take the same thing, let's take this, at very, very cold, it weighs, let's say, an ounce. When you get it hot, it weighs 1.1 ounces. Well, how did it get hotter? I mean, how did it get heavier? You pushed more electrons in it. Electrons flow out of something. The electrons, which is the black and white, they look just about like this. They flow out into the air, and the air accepts them because it wants the electrons, which is these heat little particles. When the air is warmer than the thing that it came from, it pushes them into that thing, and that thing gets warmer. All right, that's the key. And I know this for a 100% certain fact because I used to work with calibrating scales for weights and measures. And we had to get our weights calibrated every so often up at the weights and measures place. And you had to leave them overnight so that they were the exact same temperature as the room that they were in. Then they would weigh correctly. But if you took a cold set of weights in there and weighed them in a warm room, they'd come out wrong. And when I first heard that, they said, no, you have to leave them here for 24 hours. I said, no, well, for what? I said, I got to come back in 24 hours? Just why not do them now? And he said, yeah, they have to get to the right temperature. And I said, no, how could it be? And sure enough. And so that was long ago. That was close to 50 years ago. That's always plagued me. I always wondered why. But it's the electrons actually move in. I think I didn't know either. I said, why does that happen? He said, oh, we think it's got something to do with the movement of the air inside, because they put it in this thing. It's a sealed enclosure, and it's a very, very sophisticated weight device. And two things come in like this. They're like this. And then they put the weight on top of that, and then the thing moves apart, and it's on the one, and it can tell how much it weighs. Something, I can't remember, something, as I recall, it was like that. And then this would know how much it weighed exactly. I mean, it was exact, because this is for commercial trade. So, and then they had to seal them. I have a regular seal that has lead weights and all that stuff. Whenever we sealed, after calibrating the scales, we had to seal them. And so I know this is no question whatsoever, this is true. And the only reason a hot air balloon rises when you put heat in it is because the gas expands. So you're taking up much, 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 much more room with the same amount of particles, so it goes up. This, you've got the same amount of particles, I mean the same amount of room, and you're just heating it up, adding extra electrons into the mix in here. It becomes heavier because of the electrons. Every electron has a weight. It's 0.0005845 atomic mass units. I believe that's the weight. And there's 1,823 of them in one proton. And this is Dipole Electron Flood Theory right here. This is what a proton really looks like. The dark matter goes to the center, and all the white particles go around. And they're blue, green, red. They're all different colors. The tightest ones to the nucleus, the tightest ones to the dark matter are blue. Those are just held just as tight as can be. And when they go blue, and they go fast. The greens go pretty fast too. The reds are sort of hanging around out there. So they're not as tight as the real close ones. And that's why hydrogen is so explosive, because in hydrogen all you have is a little core of black and a bunch of blue, just enough blue to cover the black. And that's all you have. And when you rip those blues away, you really got to rip them. And when you hear a hydrogen explosion, the gas and the hydrogen explodes, it'll knock your ears right out of your head. Okay, this should be interesting. I haven't watched it yet, but it's what is energy made of? I've been asking everybody, what is energy made of? I give him up just because he just looks like a nice guy trying to do a good job. What is energy made of? And they're trying to figure this out. They've got a $75 million research program, University of Alberta, funded by Canada, First Research Excellence Fund, and 130 researchers, 600 graduate students. They're all trying to figure out what energy is made of. And this is Ask an Energy Expert. So let's see what he has to say. Let's go right back to here and let him talk. Here he goes. Ready? This is future energy systems. Now they're trying to come up with a way to make energy, and I think we might have one, but let's find out what he has to say.
You guys had some questions for us at the university, so I just wanted to take a few minutes to answer some of them and see what we can learn. So let's go to the first one. What is energy made of? What is energy made of? It's not really made of something, it's the property, or it's a property of an object that contains energy. So if we think about a pan on a stove, we could describe the pan as reflective or shiny, as heavy, or say half a kilogram, as metal, and we could describe it as hot, or say 300 degrees Celsius. And that measurement of temperature is a measurement of thermal energy. But that energy doesn't really change the pan. It's not like we're adding something to the pan. We're just...
All right, he's actually just about reading what the AI said. And it's wrong. You are adding something. You're adding electrons. Now let's just let him continue on.
Changing a property. We're adding heat.
Well, what is heat made of?
I shouldn't think of energy as made of something, but rather a property of an object. So a car on the freeway has kinetic energy because it is moving.
All right, listen to this now, my friend. You're talking about a car moving, having kinetic energy, and when it's just sitting there, it has no energy. Let's take a car that has batteries. When it's sitting there and it's fully discharged, there's no energy whatsoever. You try to drive it, it says, nope, you got no energy, pal. I'm not going anywhere. Right? How much does it weigh? It weighs 4,000 pounds. You charge that car to its full capacity. Guess how much it weighs? 4,000 pounds. Not gain anything. You drive literally 500 miles and it never changes weight. It still weighs 4,000 pounds. When it's empty again, full, empty, doesn't matter. Electricity has no weight. All right, listen to me, you hear this? Electricity has no weight, but electricity has a ton of power. What is it made of? What is that power made of? It's not made of nothing. It's made of those white particles, which I believe I have shown you, or I will show you, that are seeking the black ground. And they will go through anything. They will push motors. They will burn up things. They will create lightning. They will discharge until they can get to that black. If you have a ton of extra white here, that's all it can think about is getting to black. All right, and once you funnel it through your wires, you can turn motors, you can light up lights, you can drive cars, you can do anything you want. Okay, hold on to your neutrinos. Why are we so obsessed with comprehending the smallest units? Do you have any idea how much money has been spent on doing this? It's way into the many, many trillions of dollars trying to find the smallest particles that exist. Let's see if we can do a little better. Okay, I think the best way to do this is we're just going to let her speak, and I will address her comments with my comments like we were having a debate. All right, so here we go. All right, so she's going to be talking about the tiniest particles. She's a particle physicist. Now, I wrote papers on this years ago. The standard model, the Bohr model, didn't work. It just didn't work. And there's no way in the world it could work with a big positive center and a tiny couple little electrons floating around. They just slam right in. It just made no sense whatsoever. Everything had to be dipoles, and it is, and now I have shown them, as you have seen or will see. All right, I like to see proof. When somebody makes an outrageous statement, I like to see proof. Well, my outrageous statement was that the transfer of energy is from light to atomic vapor. Energy is atomic vapor. And I had everything all down, and I said, therefore, Rutherford's atom is wrong. Rutherford's atom is what the Bohr model is based on. Now, this goes back to when I first got out of the Army. And this was it right here. There's two types of intermolecular forces. They're dipoles, dipole interactions. And there's polar molecules and nonpolar molecules, and then hydrogen dipole interactions, dipole. Everything's a dipole. There is nothing but dipoles. Molecular dipole polarities, dipole moments. I don't know. I get so much on this stuff. And I did a lot of this. And I mean, I knew back then I was doing as much as anybody was, and I went all through everything. I mean, I went through all the chemistry, thermodynamics, all biology, and everything that could relate to chemistry or anything. And the transfer of energy is from light to atomic vapor. It's quite obvious. What do you think happens to light when it comes from the sun, between the sun and us? It's particles. It's atomic vapor, and it condenses into matter. It's nothing more than vapor, like moisture. It condenses into matter. This is just a simple pulsed red laser, and the particle is in here, and I'll show you the particle in a second. And as its field, which is a huge field, around a tiny, tiny, tiny particle, and that field is just gigantic, as you can see. Because you can't even see the particle. It's so small in here, you're never even going to see it. But everybody else has to glow a little bit as this huge field comes through, which is this particle of light. Now, it's beginning to accelerate. That's why it's starting to glow. And here it is in full acceleration. You see that? That is identical to breaking the speed of sound, only we are breaking the speed limit of the magnetic field of light and pulling that particle directly out. And here it's because it's going through a Venturi. Venturis accelerate things, just like the nozzle on a hose. You put a hose and you turn it on, it's got a big end like that, and it comes out, it dribbles out like that. You put a nozzle on the end, you turn it real down tight, and it does that. Identical. So what it does is it speeds up the water, or in this case light, and makes it accelerate. That's what we have here. So we started with slow light, which is normal light, and we accelerated it into super light, and then we put it through the Venturi, which is the Venturi is right here. And at that point, these particles, which are normally black and white, just like that, you see that? That's what a photon looks like. Just like that right there. These are photons. And each one of them is a dipole. Back to back, they're just like two-bar magnets. And the field is huge. The field around is gigantic. So as it comes through, it just pushes everybody out of the way. But it is stable when there's two of them together. That's a stable particle, a photon. Only one of these, if you had only one of those, that's an electron. That won't stay like that. That'll become heat, or it'll become electricity, or eventually, basically, it's going to go to ground. It's going to want to find something that it can infuse into and become part of. It's not happy being all by itself. Just remember it that way. Now, here's the red. The green are identical, only they're more energetic. Here's the green. You see it? There's the green. And they come out with these are the neutrino phases. See this color here, this one here? They gain energies as they come through the air, and then just before they actually bounce back at you, they turn into a photon. And the same thing with the red here, you see? These are the neutrino phases. And they call them flavors. They get a little more energy, a little more energy, a little more energy, and then eventually they turn into the photon as they get ready to impact whatever they're going to bounce back from. Now this is way out here is a photon. Normally you wouldn't see that, I don't think, until it was right here. But we're being pushed back because of the bounce back. You see the bounce back? Look. Right here, everything's bouncing back, and the black can't get through. The black's too big, too big. It's like this thing here trying to get through the little tiny thing. But the little white ones, And the glowy ones, they can get a little tiny thing and go squirt down here and go right through. Zip. And this comes bang, 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 and pushes these. And forces them to squirt through there. There's nothing better than this. And there's nothing to do. There's no charge. You just put a couple of pins in there to make a Venturi, and it has to go through the little tiny slit. That's it. The black can't get through, the white gets through. The white is the energy that runs a car, runs a battery, runs everything. It has no weight whatsoever. You got to harvest it right there before it gets back to the black. It's going to pull us right back into the black instantaneously. They call them muon neutrinos, electron neutrinos. Sterile muon goes by itself. Electron shower creates the shower. That's it. There's no guesses here. It's not like there's any guessing game. And it's exactly the same particles as Fermilab. These are Fermilab's particles. And the little one, the glowy one, can get very big and small. They claim it has no weight, and I agree. I can't find any weight to it whatsoever. When you see an atomic bomb blast go off and all the white ones hit the house and everything, it just smokes like this. It doesn't even move. It just incorporates these particles into it and combusts everything in there. And then the black ones come, because the black ones are inside the core, as I showed you before. The black ones are inside the core. So let's say this is all the black material. And it's not going to be one big ball. It's going to be individual little balls. You see them? Little bitty ones. There's going to be 1,823 of these little black balls, or little balls that would make the core of a proton. 1,823 ones. There's going to be 1,823 electrons, the glowy parts, surrounding that. So this will be in the center, but it is actually 1,823 little balls. And they are balls. You can see them. There's no question that's what they are. You see them? These little black balls, little white balls. This like I said, there's no guesses here. And they see the same thing. The black ones and white ones. Only they see the red, they see the green, they see the blue. We do too. We see all the same colors they see. You see, here's a red and a blue, red and green at the same time going through. Look at how powerful the green is. It reconcusses out here, just pushes the red right out of the way. Same particles, but this phone didn't have the same capabilities as the other one. And we used, this is called CMOS, complementary metal oxide semiconductor silicates, which are made to see these particles, which are light. Those particles are light. They're not what they're doing at CERN. CERN and Fermilab, they do this. They take the big ones, smash, and when they do, they come off in chunks. Like a chunk like that, and it destroys the CMOS. That's why they never could use CMOS. And I actually went to the University of Geneva for particle physics because I could never get anybody to listen to me. They did, they listened. They were very nice to me. And I said, we're doing this, and I showed them all the stuff. And they said, no, you can't use CMOS to see that. You're seeing something that, I don't know what they said. And I said, no, we're seeing the light. We see the light. You don't see the light because their particles are just way too big. So when they put CMOS, which is a little bit delicate, it's made to pick up light particles. It's not made to pick up a bang like that. It's made to pick up one of these. And every single pixel in CMOS has its own amplifier. And it's a standoff. You stand off here and you collect what is being spit out, which is photons. That's all you're picking up. It's not what CERN was doing. They were putting things in there to change, to absorb, or to push particles in. So they said every time they looked at it, it would change the outcome. Well, that's because they're either absorbing energy out, so they're changing it, or they're pushing light into it so they can see it. The way Don Lincoln put it says every time you look. Well, hold on a second. I'll show you. It's kind of funny. Watch. Here, let's see. You got the black one, which never changes. It never changes. Then you got the white one, which is or green or red or blue or whatever. It's the energy one. Now, here's what he says. If you magnify the extended one, the black one, it will look bigger. It just gets bigger and smaller because it's just a one big ball. The point-like particle, which is this red one, will not change in size, but the more closely you look at it, the stronger the field surrounding it becomes. So if I get down here and look at it, No, that's because when they say the closer you look at it, it's not closer you look at it. The more energy you put in to trying to look at it, the stronger the field gets. It's pushing back, just like our field. The stronger you push, the more it pushes back. They're pushing here. These guys are pushing back. They just don't understand. When we're using CMOS, we're just waiting for it to hit us. It's just going to go somewhere else if it doesn't hit us. It's not affecting this whatsoever. And they did upgrade CERN to use CMOS. It took 3 years to do. They had to create this hardened CMOS. And this is exactly what happened. I said, and I told the same thing to Don Lincoln at Fermilab. I said, we're using CMOS and it works fine with light. It doesn't work with what you guys are doing because you're just too big. It's too big. That damages CMOS. Absolutely, you're right. So what they did was they made hardened CMOS, which it must give it some kind of layers of, and by the time it gets to the bottom layer, all you got left is the light particles. So it doesn't destroy it. Something like that. And it took 3 years to do it. Okay, here it is right here. The radiation hard active CMOS sensors at the Large Hadron Detector upgrade. The luminosity was going to increase higher, and they needed to be able to see these things without damaging it. So it'd be increased during the long shutdown of 22 and 23 in order to increase the sensitivity of its experiments in order to be able to see it. Completely new inner detector needs to be developed to withstand the extremely harsh environment of the upgrade. So it's a so-called high luminosity, LHC, high radiation hardness, as well as granularity, and mandatory to cope with the requirements in terms of radiation damage as well as particle occupancy. Again, we're using this. This is you can hit these as hard as you want. All you're ever going to get is one of these. They're using these. They're going to hit these just like gangbusters, and they're just going to get big, really energetic blobs like this. But they mean nothing. They're just going to be bigger blobs of higher energy stuff. And I know the only reason they're doing this is to get down to this particle, to see this tiny particle, which I'm showing them. And then, can we use this particle? I think we can by splitting the black part from the white. This has a black and a white. You don't see it, but it's in there. It's a dipole. And all these dipoles come together as little tiny ball magnets. Normally you think of a bar magnet as a bar magnet. They're bar magnets like this. All right. And I ran into something the other day. Look at this. You see this? You can't, they're fighting each other. Now watch this. If I turn it this way, they go right together. Now, and if you get real hard, tight magnets, I mean, they're tight. And all you got to do is turn it 50-50. And it pushes away. It pushes away. It won't go. And you turn it this way, boom. I saw something on the internet that showed somebody doing that, and I thought, no, something's not right. And then, sure enough, I figured it out. Here it is. Oops. Anyway, they upgraded to be able to use the CMOS just like we're using. Now, just so you understand, I feel very confident that this is the correct model of the subatomic realm, and the only two particles that exist is these two. The white electron, which you can get big and small and is very powerful, and that one's just like a bowling ball, never changes, and that's the muon, and that is actually dark matter. And they go to the center of all matter, so you never see it. The only thing that bounces back at you is this. Those don't emit, they don't reflect, they don't absorb, they're just sitting in the middle. So the standard model has to change a little bit, not a whole lot. Light is atomic vapor. Light is atomic vapor. It's identical to moisture vapor in the air. The more condensed it gets, the more it turns into water. The more condensed the light gets, the more it turns into matter. And the more condensed the matter gets, the bigger the particles get. The bigger the particles get, the bigger the core gets to atoms. That's what creates these building blocks. So we have to change the periodic table a little bit. And these are the only two particles that exist. And they normally are going to be attached to each other no matter what. Now, this is an electron configuration, which they call gluons. And this two gluons back to back is what a photon is, and that's the light that I showed you. Now, neutrinos are in the phases of different color ranges as they start gaining energy before they become a full-fledged photon. And then they're going to have their full energy, whatever color that is. As they change, getting to their full energy, they go through different, like, flavored colors, they call it. You know, flavors of ice cream almost is the way they refer to it. Now, we got some changes in chemistry. Chemistry is going to change a lot because all the things that are done in chemistry are done by enzymes. They're done by enzymes. Enzymes is by life. This is what builds. They cannot explain anything above iron. The physicists, they say these particles really shouldn't exist way up here. These heavy ones, we have no idea. They must have happened in a Big Bang. No. They happen as the daughter isotopes of decay. Decay doesn't always go down. Decay can go up. All you got to do is to look at the isotope values. And isotopes are nothing more than these atoms with some more or less of these extra particles. Because they're made of nothing more than these particles. Bigger, 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 bigger snowballs. That's what atoms are made of. All right, before we go back into this to hear what she has to say, the main takeaway from this is what is this whole thing about? They want to create fusion where they can make particles come back together and give off excessive energy. Well, they have to put so much effort into doing this and so much energy into making them come apart so they can come back together. I don't think it's going to be realistic. What we're doing is with the light, as I have shown you, is we're just sending light through a Venturi, which automatically splits the light from the black and the white. So coming through our Venturi is this. The laser light comes shooting through here. There's two pins here, just like this, and they stick straight down like this. Very, very close to each other. The black balls are too big. They can't get small enough to get through that slot. These little buggers here, they go right through. Zip, zip, zip. And the beauty of this whole thing is, these with the black were attached normally. These little ones can squirt right through, and they just go snap, snap, bap, 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 and they squirt them through, and they come out of here with a vengeance. Now, the black ones are just waiting around to reattach to them. The black has to be everywhere, as far as I can determine, because they're just hanging around, waiting around for these white ones to come. And the white ones come all by themselves as showers, and then instantly they turn back into the same things they started from, which is the photons. Now, if we could harvest that white in between here and before they get back to the black, that's all you want. It has no weight whatsoever, and it's all the energy. This is what we need to do to get free energy. All right, this is what I've been showing for quite some time now. This is the accelerated light. If we can harvest that white before it gets back to the black and send it right down through a photodiode, and you could have banks and banks of these are tiny, tiny, tiny. However, if you can, all you want to do is get the white away from the black. That's what electricity is all about. Is the white has no mass and it has all the energy. You put that white into a car and fill it up, it doesn't gain any weight whatsoever. Regular gasoline is 6 pounds a gallon. So you put 10 gallons and you just gain 60 pounds. In a car, that's in a gasoline car. In an electric car, you fill it up to go the same number of miles and it didn't gain anything, no weight at all. All you did was put the white in, and the white has no mass. The black particles have all the mass, and they can't get smaller and they can't get bigger. They're the same size. And when they come through here, they come smashing through with the white ones, but the white ones can get through and the black can't. And they just keep squirting, 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 as you can see. And that is an increase of energy way over the top. Those are electron showers. That's what they've been looking for. Now, if you could do this, and it did work, and I'm not saying it will, but I think it would, And all it takes to see this is a good cell phone, good CMOS. Now this was 2012 or so, 2013 this came out. This was the Galaxy S3. And that's what all these pictures were taken with, the same phone and the same laser. It's a Bosch construction laser, CMOS, a regular construction laser, boom, 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 pulsed. And that was the red. And the other ones, Rod really did virtually all of this. So, but I know I had the same equipment here, and I used it. I didn't have his, he must have put, I don't know how many hours into this, but boy, I tell you, the work was outstanding. And he used the selfie side to take these pictures. And he put it right up and could see these. And he could, you could see all the detail is just stunning. Look at that. This is the black particles. Did some squeaked through the Venturi. Because it can be tuned to all kinds of different ways. And some black is now pushing the white. So we now know the black pushes the white. And we saw it before, squirting it through. But this just shows you how nice it squirts it and pushes it. And if the Venturi was designed correctly, when this came down, these blacks would just go just like a wall. And that is squirting in here. Now you could change the number of pulses. You could change the value of the laser. The different color is the different intensities and so forth. You all kinds of things you could do. And the structure of the Venturi is the key. And the tuning to keep this black from getting through and harvest it right over here. And if you could do that, there's a possibility you could, there's so many of these you could put in this box. It would be just thousands. And if each one of them was producing a little bit of extra energy, and it looks like they're producing a hell of a lot of extra energy, because it doesn't take much of these white particles to do a lot of work. You take these little batteries; they've been around for years. They keep pumping out the same little bits of electricity. This is it's incredible how much energy these things have, and especially when you get static on you and you come up to a water pipe or something, and snap, it jumps the air gap like. And they have some power. Electric cars and electric everything is very, very, very powerful. Okay, now we started with light. That's the key. Wait to hear what she has to say. We started with light, but not only that, instead of it just going the same speed, we accelerated it because we used a Venturi. All right, and this is nothing more than atomic vapor, and it accelerates exactly the way water would accelerate in a hose with a nozzle. It's no difference. It's a Venturi. They used to have them in the carbureted gasoline engines, and you tune it in with what they call a needle valve, and you cut back on the amount of air that's sucking through to make it more of a Venturi. Until your engine came nice and smooth, and it'd be just nice and smooth. And that's when the Venturi was doing its job. Here we can tune this to all kinds of different ways, and it can be constructed in all kinds of different ways. But the key is here, it's very, very simple design, and out came the white energy. And this is literally, and I'm not kidding you, this is a subatomic nuclear explosion. And it is an explosion, there's no question about it, none whatsoever. The particles started like this, and if they exploded, what would happen to them? The black would come away from the white, and guess what? That's exactly what happened. Here's what they are. When they hit the Venturi, kada-ba-boom, and you end up with nothing but black out around the edges and white in the center. That is fission right there, breaking apart, and that's coming back together, fusion. Now, you don't have to use deuterium and tritium and all of these other exotic atoms that they want to break and make into stable molecules and give off a bunch of excess energy. In order to break them, they have to put in a whole bunch of energy. They're not just going to fall apart by themselves. First of all, you have to start with some really exotic stuff, deuterium and tritium. That's not something that just hangs around. And then you have to have all kind of exotic equipment and everything. And then you have to figure some way of harvesting it. And then you have to distribute it. What I'm talking about is right here, can be put in a little box like that right there. No wires, no plug and nothing. You just plug right into it, anything you want. Turn it 50 cycles, 60 cycle, 110, 120, 220, whatever you want. AC, DC, USB, MAC, KEY, ammo, USC, anything you want. And seal that up so that it can go in the rice fields or in the fighters to take it with it. And you should be able to get so much energy out of a box this big using bazillions of these little lasers in here, because this is the size of a head of a pin. I would think you'd get a ton of energy, but I don't know. Somebody's got to work on this. This has been many years now. I've been asking for somebody to step up, and it hasn't happened yet. So I'm hoping this will. And we're all looking for the same thing. We're looking for solutions. And if we can do it for less money and get more out of it, it's more opportunity for everybody, and it's more. Energy is the key to everything. Energy is the key to everything. And if you can turn from just barely light, all right, which is this. Back here, you can't even see the light. Up here, it starts to see, you see it because it's just starting to accelerate. You can turn that darkness into this. That's energy. That's electron showers. I'm sure she's going to know about electron showers and sterile muons and Cherenkov radiation. That's what we're doing, only we're doing it in the air. We don't need heavy water. Look at this. This just came out today. Climate change is slowing Earth's rotation. How would they come up with that? They say it's because the glaciers are melting and all that water is coming down to the center of the Earth and slowing the rotation. That's crazy. Here's the deal. We are burning so much on the surface of this Earth that the atmosphere is expanding like blowing up a balloon, literally blowing up a balloon. And that's why this is happening. All right, they're talking about the Greenhouse Gas Commission. Okay, that's this right here. Now, I don't want to have to go through the whole thing talking about the greenhouse gases, but they're going to enter a new, I thought I commented on this. They have no comments. Interesting. Now, this is the Earth. And this is California over here. Now, this is from NASA. Okay. Now, here's what they're showing. Is the pole up here. Up here is the Arctic region. Now, these are the central core of the Earth. So the Earth is spinning basically like this. So these are the most impacted. This is sort of a little swirly deal going on up here because these things only move a few thousand miles, whereas these are at 25,000 miles or more a day. These are only going a couple thousand to do the same thing. So there's a little bit of a swirly action going here. This is totally different, and you'll see it. Now, I have this running very slow. Hold on, let me turn the lights down low. Hold on. Sometimes that has a better effect. Now, don't forget, this is the swirly part. This is California and the United States, and this is where weather patterns get set up. All right, this is the impact region, and I can tell pretty much that this is the sun is hitting this edge here. Now let's watch this. All right, now you see, whoops, hold on a second. Too much to drink over there at the National Weather Service. Hold on, here we go. Now, you see up here, this is where all the swirling's going on. You don't see it here, you don't see it here. You see it? This is just like impact zones. This is where weather patterns are set up primarily. All right, and we got a lot to learn about our planet. All right, I'm just going to make my claims, very, very simple claims, that the Earth is like one big ball of mass. All right, now I'm going to play this forward very slowly. All right, this is the surface of the Earth. It's one big ball of matter. This is atmosphere. All right, this is one of the poles, which is the North Pole. The South Pole is the same situation, only on opposite polarity. Now, these edges down here, as they spin, they're making a complete rotation through all the particles that are in space. All right, space is saturated with particles, absolutely saturated, and it is crushing down against our atmosphere here, creating extreme amounts of heat out here. It's almost I think it could be 3,000 or more degrees in temperature out here. It's so hot, the ionosphere, right where it hits the exosphere, which is just, it's not a vacuum. No, there is no vacuum. When light comes towards Earth, all right, this is my little drawing here. When light comes off of the sun, it's coming off as particles. Light are particles. I showed you these, or I will, no question whatsoever, they're particles. When they're traveling through space, they're still particles. They may hit a little of this and a little of that, bounce field against field, but and sometimes they may bounce and just stop. But normally they're going to work their way through this ether, this swamp of particles, which is nothing more than light and dust and all the debris that's in space. And it's everywhere. Don't tell me it's not out there. No. And I will show you a picture taken that shows all of these fields. Now here's what happens. The light is coming through, fairly, it's not a vacuum. No way in the world is it a vacuum, but it's not dense. However, right here, you hit our dense space. And right at that point is where these particles scrub like hell. And they literally scrub and create heat. And that's where right now they're saying the Earth is slowing down. Well, yeah, the more you pump it up like this, the more it's going to scrub. The more it scrubs, the more it's going to, slowing down. It will. The pumper up you get, the slower down you go. All right, and that's us. Right now, the gases are about out here. Well, maybe they were about out here 100 years ago or 50 years ago. And they want to pump, every time you burn something, the size difference between something that's in the ground not causing any trouble at all, oil, gas, coal, whatever it is, it's just laying there. It's just doing nothing. All of a sudden, you take it out and you turn it into gigantic, huge amounts of space. It's got to go somewhere, and it goes here. And it will not just leak into the universe. No, absolutely not. This is a scrub zone. This is not some it'll just go off and it'll go on its way. No, absolutely not. It is being scrubbed into that's why this is so hot out here. People don't know that. They think, it's got to be zillion degrees below zero. No, absolutely not. Let me show you. Now, this is the kind of fields that are out in space. Everything that's traveling through there is being slowed down by these fields. There's no question about that whatsoever. Light is slowing down through these field mediums. This is not empty space, not by any means whatsoever. First of all, because of all the particles. Secondly, because of all the things that are spinning in it, creating these huge magnetic fields. Particles don't just flow right through that without being a couple things. They get warped. They know that. They say, oh, then we know there's matter there because they're getting warped. Yeah, because they're coming through here, twisting through these fields. No question about that. But they're also slowing down as they pass through just in these areas. They're slowing down. There's no question about it. So this thing that light never slows down, it's insanity. Plus, I'm showing we can speed it up. And that's not even in a vacuum. If you don't understand that speeding up, I don't know what to say about your ability to think. And if you don't understand that is much more energy than back here where it still was here. There's no energy to speak of until it was pulled forward and crushed. That's when you get the energy. And this is literally a subatomic nuclear explosion. The black separated from the white. Here it's turned into a particle. Well, it was a particle all the time. You just didn't see it. And here it starts to stack up, gets more and more and more energy called neutrinos. And then it all of a sudden turns into a photon right about here, as all these do too. They were all in the air. You just couldn't see them. And the only reason you can see this one is because it was straight head on into the Venturi. There's the Venturi. Absolute straight head on. All these other ones in the air, you just never saw them because they just didn't have enough energy to be seen. This is the only one. Now, so we know we got acceleration. We know we got enormous amounts of energy. We know the space is saturated with these fields. We know the sun, this is a solar eclipse. So the moon being here is real close to us, and its size overshadows the sun. So it's not the same size as the sun. As somebody say, oh, I didn't know the moon was the same size as the sun. No, it's because it's in between us and the sun, which is so far away. It is basically the same size. But you can see all the stuff. Those are all particles. Those are particles. They're not just nothing. And that's all coming out of there. And some of these are chunks. Some of them are not tiny, tiny, tiny particles like light. But most of them are, I would think, but I don't know. So now, what do we know? We know light is made of particles. We know they're coming. What about the temperatures on Earth? Here we have the Earth. Well, out here we have the exosphere. It's cold. Outermost layer, very low density. But there's still a lot of stuff out there. Then all of a sudden you get here. Well, what is going on here? This layer appears the northern lights, temperature 1500 degrees Celsius. That's like 2,700 or so. And this is where the meteorites burn up. It all depends too on whether they come in with this rotation of the Earth, so that they're going with the stuff, or they go against it, so they're doubling its speed, basically, that type of thing, or they come straight down, or, there's a bunch of different ways. And so not all meteorites are destroyed. I have some here that are not destroyed at all. Now, this, though, is hot as can be, 2,700 degrees. I'm going with Fahrenheit. Down here, at this one right exact layer, is where the dipole effect comes in. So this, right up here, is the hot particles hitting and scrubbing. This is the scrub zone. It's hotter than hell. Scrub, 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 scrub. And the light comes in, and this scrubs. It's not, it won't go, it won't leave. It won't just leave. It's scrubbing. All right, so, but when it comes in, it has the other side attached to it, which is driven down, and this is where the cold is, minus 80 degrees Celsius, right below. It's just like that. It's a dipole. That's 2,700, and then over 112 degrees or so. So it's 2,700, 2,800 degrees difference between these two layers. So you got hot, you got cold, then you get hot again. That's us. All right, that's why we're getting global warming. It's hot, cold, hot, and then the Earth is literally ground, which is cold, because that's what the electrons, they'll be very happy to get to here. Once they get here, they're happy. They'll go right through you. If they collect in the air, static, lightning, all that stuff. It's nothing more than just too many electrons. Nobody wants them. They get in a big ball, and it comes down. Now, what about here? Minus 80 degrees. Here's what's going on right now. It's getting hotter and hotter as this gets bigger and bigger and bigger out here, scrubbing harder and harder, and it's actually literally slowing the Earth down. I don't see it wouldn't. It's getting bigger and bigger and bigger, and it's going to get scrubbed harder and harder. Now, we get more and more electrons out here. It gets hotter. That means this is going to get colder. That means this is going to get colder, not hotter. Because the hotter this gets, the colder this gets. And what happens? It condenses too. The more compression, the more condensation. What does condensation do? It makes water turn into ice. They got globs of ice coming now the size of basketballs. It's going to get worse and worse and worse. The more compression, the bigger and bigger and bigger. And the colder and colder and colder. And then they have no place else to go except down to the Earth. And the Earth will absorb all of those things. That's where they want to go. It's called ground. Every single electron would love to be down here in the ground. All right, so first of all, why is it so cold in the Arctic and the South Pole, the North Pole and South Pole, compared to out here in the edges of the Earth? It's much warmer. Well, there's more scrub. That's a hell of a lot of scrub. That's a hell of a lot of scrub. There's not a lot of scrub up there. It's just sort of going around little loopy stuff. There's a lot of scrub here. The more scrub, the more heat. As simple as that. It's not a big mystery. There's no mystery here. And again, this is not empty space. They showed us like it's empty. There's nothing here. No, no, no. It's saturated with stuff. Now, not only that, this is where our 2700 degrees is. All right, and then just below it in the cold, it gets real cold. Now, here's what's happening in reality. The sun is out here, has the same situation we have. It's moving through space, spinning and rotating and ripped through the arm of the Milky Way and all that stuff, which I'll show you in a second. And it radiates all that stuff out. I just showed you before the solar eclipse. All of that stuff is coming out. Well, what happens out here? First of all, the surface of the sun, which obviously is behind the moon way out there, the surface of the sun, they say, is 10,000 degrees. 10,000. That's not hot. Guess how hot it is out at the corona, which is a ways out from the sun, where it scrubs, just like our Earth scrubs the ionosphere. Well, they have their own ionosphere. They call it the corona. Millions of degrees. They have no explanation for this, none whatsoever. They want to have a big, huge mission to go out there and explain how could this big difference in temperature, only 10,000 on the surface and millions out here. Well, the reason is the scrub. And the same thing with global warming. They don't understand global warming is the scrub. It's not that the carbon is holding a whole bunch of extra molecules in here which warm up the Earth. No. Carbon is a byproduct of combustion, yes. CO2, carbon dioxide. But they're burning things that were solid and making them blow up like this. So the more pressure they put on this surface, the hotter it's going to get. The hotter it gets there, the colder it gets just below. The colder it gets below, the hotter it gets just above the Earth. And then the Earth will absorb that. But the Earth will grow in temperature too. The oceans will increase in temperature. The land masses will increase in temperature. The things that should be wet and moist will dry out. Some other areas will become extremely soaked and wet and moist because they're going to be compacted, because everything here is going to be under stress and compression. It's like you're blowing a basketball up and as you're getting ready to pop. The sun is in the same situation. On the sun, it just burns normally, and nobody's up there burning extra stuff in the sun. The sun burns because it's spinning through the universe, and it's so big that it just, everything on here just bubbles and combusts at 10,000 degrees. But out here it's millions of degrees because all the stuff is spitting out, and its scrub makes it millions. There's no big mystery here. It's not even close to a mystery. And the more we burn and create gases, the hotter it's going to get, and it's going to be terrible for crops. They're talking about this greenhouse gas emission. They're just going to tell you where it's going to be unlivable very shortly. You know, the solution to this situation is to stop burning. How do you stop burning? You have to get into free electricity or some kind of electrical production that doesn't require huge energy emissions, which is gases. They're greenhouse gases. They're gases that expand our atmosphere. All right, don't forget, this thing is gigantic. They get fantastic collisions, yes, well, they should for the kind of money they're spending. Here goes.
Kilometer ring. I may have mentioned the whole thing is 100 meters underground, and I'll show you what an image of that looks like so that it's safe for people to be walking around on the surface, and you know, everything is.
All right, she's saying it's safe for them to be walking around on the surface. Why wouldn't it be safe for them? Well, the reason is they're actually creating atomic bomb explosions under there. When an atomic bomb explodes, what kills you is the radiation chunks. All right, not light. The light is just little bits. That won't kill you. That'll just make you light up a little bit. But when you get hit with these things like here, that's what kills you. That's nuclear radiation. So they want to be so deep, 100 meters in the ground, that everything in front of it will stop that from coming up and hitting them. And they have to wear special badges for a certain amount of time. They can only spend a certain amount of time around this, and even that, I wouldn't. If I was them, I wouldn't do it. Anyway, they want to keep the people on the surface safe. It's 27 miles or kilometers. What'd she say? I think she said 27 kilometers. So they're at the dawn
of the Grand Canyon, so that you can get
27
a sense of it. It's essentially on the scale of the Grand Canyon. So this Large Hadron Collider accelerates these protons to close to the speed of light, and then has really fantastic collisions at multiple places around that 27-kilometer ring.
We use that.
I may have mentioned the whole thing is 100 meters underground, and I'll show you what an image of that looks like so that it's safe for people to be walking around on the surface, and you know, everything is happening underground. But we make absolutely spectacular collisions that we then have to analyze. And I'm going to say just a little bit about how that process works. How do we try?
So am I. What are they seeing here? They're just seeing debris. These things are so gigantic that when they slam together and they hit, as they cross paths, they just throw particles everywhere, and they get all kinds of debris. And so then they have to analyze them forever, yeah. Try to figure out how this happened. Well, I can tell you how it happens. Is the particles are nothing like they think. They're not just these big, huge particles that slam together, and then they get a lot of debris. And then they figure, well, there's got to be something in there that we can analyze. And they did, and they found that the tiniest debris that it was the black and white particles. All right, and here it is right here. Same ones Fermilab and CERN found is the same ones we found, only we used light. So we didn't have to dig through all that debris. And here's what they see. This is all the kind of goop that comes out. X just means it could be this big, it could be that big, it could be this big, it could be half that big. But they see photons, and they see the particles of light that we see, the green, the red, and the blue, but they don't know where the dark matter is because they don't see it. Dark matter you only see when it's on top of white matter, and I don't think they would know even to look for it that way. But that's what I found. The only time you see dark matter is if it sits on top of the white. Dark matter's all over the place. It's all over here, but it's just, you can see it's snuggled over the top of some dim white here. It's trying to work its way in just as soon as it can to get back into the white. But you can only see it if it sits on top of the white. You'll never see that dark matter because we're in the subatomic realm. Subatomic means below an atom. Well, what does that mean? An atom is a stable ball, a big ball, compared to these. These are one of these. There's a black one and a white one together. And this is, we're seeing the black one here, just floating by themselves. They're called sterile muon. Now, if this was a proton, the thing would be gigantic, it'd be this big. Huge, compared to what we were working with. Totally different situation. Totally different. So you're never going to see that black once it's in the center of the white. This is what you will see every single time in every single atom. That's why they have never seen the dark matter. They examine this and they say, oh, this is all white matter. This is all white. There's no darkness in here. Well, when you smash them together or in a collider, eventually you get down inside to where the dark matter is. And there it is right there. And that's Dipole Electron Flood Theory. Right there. Now, there's only one other possibility, is that you got black in levels. Now watch, you see how it's, here I have the dark matter, dark energy, which is the black side of the dipoles, all collected to the center. Now, there's another possibility, which is this, where you have a central core which has plenty of particles surrounding it. So in other words, that black would be completely surrounded by the blue. But then there'd be another layer of black. And then the green would be attracted to the black, that type of thing. So it would have layers. I'm tending to go with this. I go with that. Regardless of what it is, this is the only two particles that exist. Their particle zoo that they show as the standard model is just, it's not real. All it is these two particles in a whole batch of different configurations in the zoo. All right, it's the only ones that exist are the black one like this, and these little red, blue, and green ones that are the energetic part of this. They didn't see these. They don't see those. This is like just lost to them. But when you work with light, like we did, there's nothing lost. Everything is found. All right, where's the one? Here it is right here. That's a photon. And this one's getting charged up because it's coming through the air this way. And if you can see, I don't know if you'll be able to see it or not, these little white particles in front there, that's why this one's getting bigger and glowing. And this one's getting less. Now, at a certain point, that'll get so big, it'll go flip, and that one will come in front, and this one will go to the back. It's an upspin, downspin, they call it. And you see here? Here it is right here. That one there is this one. This one here is that one. And this one here is glowing because it's impacting with what's in front of it. And then when it gets to the Venturi, which is here, it actually just separates completely from the white. The black can't get through. It's really literally as simple as that. I know it sounds stunningly, ridiculously simple. But when something is stunningly, ridiculously simple, that's just the way it is. And that, my friends, is just the way it is. All right, so they're trying to figure out how they can see these particles.
Particle detectors. These have been described, they're essentially exquisite cameras that have amazing precision. In some ways, I really think that the analogy with a cathedral, it makes sense, that the equivalent of a modern day cathedral for a particle detector. The Atlas detector that I work on is 6 stories high, and it's 100 meters long. It's the length of a football field. It has hundreds of millions of electronic channels, and it has the job of trying to take the collisions that happen inside. All of these lines are representing particles streaming out from collision interaction points from actual data that was taken in 2016 at the Large Hadron Collider, and try to make sense of it. Let us actually work with these particles and understand what came out of the collisions. What is it that was happening?
That's almost 10 years, 2016. When I showed him this stuff in 2016, I sent all this stuff to Don Lincoln. I think I was going to University of Geneva, at that time, maybe I think it was 2016. It might have been 2017, but it was right in that area. And I showed them all the same stuff we're doing, and they were very nice about it. They weren't nasty, saying you're an idiot. At first, they came across sort of like that, but nice. And they're just saying, no, you just don't understand. And they were good. They said, no, that's something reactants, or I don't know. They gave me all kind of words, and I said, well, no. Then I explained to them what we're doing, and it ended up that they said they would follow me on Facebook. I'm not kidding you. That's how it ended up. I said, can we do something? They said, no, we'll follow you on Facebook. And then I was thrown off of Facebook, so I'm back on now, but I don't do much there. Now, I found it very unproductive. But anyway, here she goes.
And you can think about the basic design of a particle detector being an onion. It's different layers, and the layers have different jobs. And what we do is, taking into account the ways that these particles, we can have thousands of them that are created in our proton-proton interactions, trying to understand how those particles interact with the different components of our detectors. And we're essentially detectives that look at the different signatures. And this is showing you, if I'm a particle that's created at the center of one of our detectors, I stream through different kinds of detectors as I make my way out from the center outside, coming out. And I actually, if I'm a particle that's created at the center of the detector, I myself might be traveling close to the speed of light through these particles. Or if you're a photon, a massless particle, traveling at the speed of light. And the cool thing is, the detectors have been arranged so that different kinds of particles that can be created, and I just have some example names of a lot of the stuff that we make when we make these particle collisions, they leave different signatures in these different layers of the detector. I know that AI, artificial intelligence, it's one of the big things that it's certainly a topic today, and along with machine learning. We've been taking advantage of this and using it to have great results for actually a long time in particle physics, developing algorithms and teaching those algorithms to learn to recognize what different kinds of particles look like, so that we can.
I got to be honest with you. I have found AI to be automated indoctrination. It's not right. Many times I have found it's not right. It's not right about particle physics either. It repeats to you what all these people are saying, all this peer-reviewed stuff. The peer-reviewed stuff now is so suspect that everything I have shown you, if you can't see that they're wrong, then you belong there. You belong at Yale.
We can learn from the collisions that happen in our detectors.
To continue watching this video, click the link in the top left or in.
Okay, I'll try to put a link to this, but you can see that they just don't understand what even the particles are made of. And what, to see this mess here and think you can make something out of it by smashing things to bits, and looking enough times you see the same wheels coming out of here that means something. It does not. What we did is meaningful, extremely meaningful, and needs to be investigated. It needs somebody to stand here and say, well, Roger, let's see what you did. That's all I'm asking. And then take a close examination of light from a pulse red laser. And this is the pulse red laser right here. And this is how it was taken. Pictures with the selfie side of a Samsung Galaxy S3. And, again, Rod Warren did all of the fabulous work here. I used different gratings and different stuff. He used the Venturi, and he designed it and created it. And it is, I think did I show you this? I must have. It's where the laser light comes through, and it's these particles right here. They can be either green, or they can be red, or they can be blue, or they can be any color as far as I'm concerned. Where's the red? Here's the red. All right, but they have the black and the white attached, and they are tight. When they hit here, the black backs off, the white squirts through because it's small enough to squirt through, and these slap the white through. We harvest that, right through here, so it's slap, 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 and it drives it in down, just slap, 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 just like pulsating energy into the batteries or wherever you want to use it. And it could be carried around in that little box that I was showing you, something like that, something similar. Here's the whole thing right here. This stuff is a dime a dozen. And if you could, once it turns on, it should be able to create its own energy to reproduce itself, to keep the laser going, and the rest you use for whatever you want. And it would be portable, no grid required, no nothing, any voltage, any amperage, any, type of port you could put in there you want. And totally. There's no way you can get hurt with this. You're only working with light, first of all. And once it's inside this metal enclosure, it's not coming out of there. Even though you're doing this. Now, Rod did this for 5, 6, 7 years or more. And I don't think anything happened to him. It comes back together like instantly. Now, if you put your eyeball down there, well, that'd be a whole different story. But this is very, very tight, small distances. And this is what comes out. These are the Higgs fields coming out at you. He's taking a chick. And these little spritzes are the white particles. And then they hit the black particles and they turn into the Higgs fields. Higgs fields is when the white recombines with the black. You want to see one? Look at this. I got one here. Maybe I don't have it here. I call it Higgs on steroids. Hold on a second. You see this? Rod must have spent, I can't even imagine the amount of hours he spent doing this. These are the white particles coming in. Now, normally they just cascade out and throw out all these little disks, which are, I believe, the white particle, which is so small you can't even see it in here, is hitting black particles. See, you can see some little black ones in here. Now, I believe they're hitting the black ones and they're just spinning. And they spin in a certain direction. It's called the right-hand rule. Now, you see these little spritzes? Watch this one right here. This is the cool one. You see it hit this edge of this disc? I think this specific one is creating this disc. And when they spin like this, the field collapses into itself and forms this circular pattern, these Higgs fields. Isn't that something? Look at that. All right, now here, you want to see what CERN puts out in Fermilab? Here's theirs. This is from Fermilab. Look at what we got. Now, why do you see so much red here? Why do you see why so much red? I could tell you exactly why. What happens is they're trying to make head-on collisions, almost impossible. Out of 25 billion particles or so, they may get 25 to hit, if they're lucky. Now, why? And why so much red? Now, don't forget, Dipole Electron Flood Theory says that the red particles sit on the outside. All right? The blue, when they take off, they're gone. They're not coming back. The green, pretty much the same thing. You have to really bang them to get them going. The red, you can push those around. So if I was to come in here and hit this thing, not quite head on, and hit it like this, the red would go flopping around, but it wouldn't go forever. It wouldn't go away forever. And that's exactly what you see here. You see a lot of the red flopping around because those are the red particles getting knocked around as something comes by. But occasionally they'll hit really head on, and the blues and the greens and the yellows will take off and they don't come back. The reds, they just sort of hang around because they're just getting sort of banged. Normally they don't hit. Here's the deal. They expect when they hit a head on, they just come in and bang head on. That's just not the way it works. Huge field around her. It's like a rubber ball. And this one has the same thing. They go boing, they go boing, They go bang. When they do that, they just knock the red ones around a little bit, and they just come back to where they were. That's what theirs is. I showed you what ours is, and ours is real. This is actually physically what happened. Those are Higgs fields on steroids, my friends. And they are not, they're exactly opposite of what they say in physics. They say the Higgs fields collapse and give way to the black and white particles coming away. No, it's the the white coming back to the black. That's when you get the Higgs fields, and you get them on both sides. Watch this. I missed this whole thing for once. Watch this. Coming down here, you have this is a Higgs field. That's exactly like what the Higgs field is. See them? Higgs, 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 Higgs. They're everywhere, and then they show up here on the other side too. It's nothing more than this one getting separated and then coming back to another Higgs again. You see, it comes through white, and then it just turns back into a Higgs. On the other side, it was a Higgs, and here's where it gets crushed in the Venturi. It's squirting back out and turning back into Higgs again. Very interesting stuff. To me, it is. And, of course, I showed you that the black will, in fact, push the white in front of it. The white can be pushed. All right, and the black can push it, and the black is nothing but a solid mass.